By the end of this video, you understand an algorithm that makes searching through possibilities significantly faster. Suppose you have 8 boxes and only one contains a prize. Classically, you might check boxes one by one, testing each option in sequence until you find the right one. But unlike classical computers, a quantum computer doesn't store each box separately. Instead, it prepares one quantum state that represents all 8 boxes at once. So in this case, it's not holding 8 boxes individually. It's holding a superposition of all of them until measured. For 3 qubits, we don't track one state, we track all 8 at once. And after we apply Hadamard's, every possible outcome gets the same amplitude. So that means everything is equally likely. Now we move to the oracle step. This is where we mark the target state. Let's say the target state is the 7th box out of the 8 boxes. In binary, that should correspond to 110. Since we're using zero-based indexing, the 7th box is index 6. But wait, if we only change a sign, how does that even help? This setup might seem a little arbitrary right now, but the diffusion operator will tie everything together. All of them are literally the same value, well, except one. But how does it help? Well, the diffusion operator reflects everything around the average amplitude, so we calculate the mean, which should come as 0.2652. Think of the mean as a mirror. This equation reflects each amplitude across that mirror. As the target state's amplitude grows, the amplitudes of the other states shrink. And there we go. We found our answer. The oracle identifies the target state and the diffusion operator amplifies it, making the target state more likely to appear when measured. Okay, all that theory is cool and stuff. So how do we build it? How do we see this in action? Let's see the core of it first. Firstly, the state will be initialized by Hadamard gates. Then the oracle function will flip the target state's sign. Then the diffusion state will amplify the target state. Do this over and over and over again. And eventually, the target state becomes more and more likely to appear when measured. And that's Grover's algorithm. All we did was repeat 2 steps, flip the target, then reflect everything around the average, and the answer slowly rises out of the noise. Bye.